Okay, so I think we're now live again. So, hi everyone, welcome back to another edition of Quarantine Thermo. We're very, very excited to have Professor Dvira Segal here with us from the University of Toronto. Before we get into it, just the usual announcements for people that are new to this format. Dvira is going to speak uninterrupted for 45 minutes to an hour. And then at the end of the talk, we'll have questions from the audience. So if you think of any questions or you have anything that you'd like to know more about, please just write your question in the YouTube chat and I'll relay the questions to Dvira at the end. Without further ado, let's get on to the science. So Dvira, I'm sure, is familiar to many of you. She's an expert on many things: open quantum systems, quantum transport, full counting statistics. Recently, she's been making some very interesting contributions in the area of kind of fluctuations and thermodynamic uncertainty relations. And so she's going to be telling us all about this in quantum transport at the nanoscale. So please, Dvira, go ahead.
Thank you very much, Mark, and I would like to thank all the organizers behind the scenes, John, I guess. So thank you very much for the opportunity to share our work here. This seminar series has been really great for myself, for my group as well. So I will talk about quantum transport at the nanoscale, and I will focus on the thermodynamic uncertainty relation, which I believe is of an interest to many in the audience. So a little bit of an introduction. My name is Dvira Segal. I'm here at the University of Toronto, so here it's morning. My appointment is at the Department of Chemistry. I'm also affiliated with physics. And as you can see in these little pictures below, I guess this is already sort of an outline of the talk. Quantum transport at the nanoscale, in order to understand the thermodynamic uncertainty relation, obviously we need to understand current and its noise. So this is this picture at the center. But what I would like to highlight in my talk, and that's a work that was published about 2 years ago, I will go over it with some details, is that if we want to understand the thermodynamic uncertainty relation, we have to think about the full probability distribution function, not just about the first and the second cumulant, C1 and C2 here, of this probability distribution function, but furthermore, we have to think about higher order moments here, C3 and C4, and so on, and I will talk about it. And at the left side, you can also see a picture of the experiment that our collaborators had performed with the idea to measure electronic current noise, and eventually one can use it and also study the thermodynamic uncertainty relation. So before I begin, I totally agree with Andrew Jordan, who presented last week, that while this seminar series has been really great, we are still missing a little bit of the social element of conferences. So usually in conferences, we just chit-chat a little bit. So here's my part. I'm originally from Israel, but in the last 13 years or so have been in Canada. So here's a map of Canada. Usually when I go to conference and people are aware of Quebec, maybe Ontario, and if they are really knowledgeable of Canada, they will know about Vancouver and British Columbia. So I just wanted to show the map, and you take a notice that there is something in between. You can see the scale, several provinces, as we call them. Probably you have never heard of them, Saskatchewan, for example, and furthermore, some Atlantic provinces and territories and so on. So here is Toronto, right on Lake Ontario. So you can see there is a lot beyond. Rochester, where Andrew Jordan from last week talked, is also on Lake Ontario from the south side. And if we want to visit each other, we have to go through Niagara Falls here, sorry. And that's, of course, the border now is closed. So that's for geography class. And as for the university, it's really great. It's a beautiful place and a great place to work. So just some pictures. Hopefully, you will be able to visit me in the future. And obviously, when we work in chemistry or physics, the buildings are not as amazing. They're still very functional, modern, useful. So that's the Department of Chemistry, a little bit more modern, and the Department of Physics. Yeah, doesn't look like that nice tower. And again, just before I go to the serious part, I guess last slide of entertainment. A little bit about physical distancing in Canada. So every country, municipality, I guess, struggle to educate the public how to keep the right, healthy distance between us. So you have to use concepts that people are familiar with, and we Canadians, we are very familiar with our loon. So you can see it's all on our coins. So 3 geese apart is a very clear explanation. I can clearly imagine what that means. And similarly, the hockey stick, every kid in Toronto and Canada has a hockey stick at home. So that's a very clear measuring unit for us here. Okay, so with that, let's begin the actual talk. First, I would like to thank great collaborators in my group. There are other people in my group. I just listed here the people who contributed to this project. So I'm going to begin with BJ, hopefully he's in the audience, a former postdoc and a great collaborator. I'm very grateful, and it has been a great path together. So BJ is a former postdoc and now an assistant professor at ISER Pune. And in fact, he's the one who had introduced this project of the thermodynamic uncertainty relation into my group. We have been working obviously for a while on quantum transport and fluctuations, and he's the one who noticed this new area developing and came up with this project. Chava, she's a graduate student in my group. She's almost finishing. She has been working on full counting statistics, cooling devices, and she has been involved in this project with the experimentalists on the analysis of the data for the thermodynamic uncertainty relation. Junji is a postdoctoral fellow in my group. He has been involved in many projects, very creative and very productive, and I will talk a little bit about his project in relation to the uncertainty relation. Anki is a former undergraduate student, and he worked on anomalous short noise. And I will talk about this project because if you want to understand the experiments related to the uncertainty relation, we have first to understand the behavior of short noise, and what we actually encountered was what we coined as anomalous short noise in atomic junctions. And last and of course not least, the experimental collaborators, so Professor Orenthal and his former graduate student Ophir from the Weizmann Institute of Science. We worked on several projects in the last few years, and we learned so much from them. So yeah, that has been really great. And of course, the funding agencies who give us money, the NSERC, Canada Researcher Program, and the Center for Quantum Information and Quantum Control in Toronto. Okay, so still a little bit of an introduction about my research. So it's my impression that the audience are all interested in open quantum systems. So here's our general scheme. Everyone is familiar with it. We have a quantum system. Here is a sketch with different, say, electronic states, vibrational states, and the system is open. Yeah, it's coupled to, let's say, fermionic reservoirs, bosonic reservoirs, exchanging energy, exchanging particles, and there are many intriguing aspects to this system. So my impression from the discussions here in this seminar series is that most of this community is thinking about quantum thermodynamics. I wanted to mention other applications that in my group we have been working on, thinking for a while. So here there are just these 3 pictures. I picked them from the literature. There are, of course, many other examples. But these are representative case studies. So here at the right, it's an experiment from the group of Lathav and Katarman at Columbia University, and it's about charge transport. Charge transport in a single molecule. So it's really not to scale. This is an electrode, an STM tip, and that's a substrate. And in between, a single molecule, which is, I guess, covalently bonded to the electrode. And the numbers here correspond to how many benzene rings you may have in your molecule. So they attach this single molecule and they measure the electrical conductance, IV characteristics, and also, as you can see here, thermal power of this molecule. And this is an open quantum system, yeah, because if you think of the electron, it's a quantum system, but we have to think about these reservoirs as well. And furthermore, there are internal degrees of freedom for the molecule and for the surrounding, the nuclear motion. And if it's in a solvent, we have the surrounding bath. So that's studying such systems has been one of the projects in my group. From the other end, so it seems like almost the same type of setup, or it is actually the same type of setup with 2 electrodes, the STM tip from above and the substrate from below. And again, a single molecule, but now it's an alkane chain, which is a poor conductor for electrons. So in fact, what they've done here in the group of Pramod Reddy from Michigan, they studied vibrational heat flow through this single molecule. And of course, it may be in the classical regime or the quantum regime, but again, studies of heat flow and specifically vibrational heat flow has been an area of interest for my group. And in between, that's more related to the most recent talk in the seminar series, QED system, where we couple a matter component, whether it's an atom or a quantum dot. Here, these are double quantum dots, and you couple them to cavity, and you can realize all sorts of light matter effects. Here, it's from the group of Jason Peta from Princeton, realizing a micromason. Yeah, so all these are open quantum systems, and the focus here is indeed on transport, understanding how the properties of the interface, many-body effects, being far from equilibrium, affect the transport behavior of the system. So this is probably, this slide is probably too busy. Don't go over it, just the titles. Again, I just wanted to mention sort of the philosophy of our work. There are many interesting challenges involved in studying open quantum systems. The fact that there are multiple reservoirs out of equilibrium, question of fluctuations, of course, many-body interactions. So what I wanted to mention is that you really have to go between these three topics. It's interesting to address fundamental questions, but of course, your ability to address fundamental questions on dynamics, on quantum thermodynamics, is limited by the method, the technique that you are using. If you have a method which is, say, perturbative in a system-path coupling, yeah, your predictions or your understanding is limited in that sense. So this brings us to method development, methods that are capable of pushing, these boundaries, maybe treating the strong system-path coupling or treating many-body effects more accurately. And of course, you have to pick your fights. Yeah, you cannot, it's difficult to address all these challenges, so different techniques may be better in different ways. So again, to address fundamental questions, we devote time to method developments. And once you have a method which can, let's say, more accurately treat, say, system-path couplings, you can continue and address questions of applications, come up with novel applications, whether it's for charge transport or thermoelectric, optoelectronics, and so on devices. And of course, go back to fundamental questions and think again about those. So with that, I'm almost done with the introduction. Just one more slide on the different questions. As you can see, the title was a charge transport. So different topics that we looked at in the or have been looking in the last couple of years. So I divided them to three areas, but it's very rough, and of course there are different ways to divide it. We have been looking at, we have been thinking about electrical conductance, or more generally IV current voltage characteristics. So here is a schematic setup, and here's an example of an application. So this is to reproduce some aspects of the experiments that I've had in the previous slide from the group of Lathav and Kataraman or others. So what do we have here? We have the two electrodes, and in between them we have a molecule depicted here with these hexagons corresponding to sort of monomers in the molecule. So one of the main challenges in this community is to be able to treat electron vibration coupling. And what does it mean for charge transport? If we freeze the nuclei, then we can treat the problem as a scattering problem, and we can come up with good predictions. But of course, once we allow nuclear motion, once electrons couple to phonons in the system or outside, then we can realize new transport mechanisms, and understanding this crossover between transport mechanisms has been, it is an interesting and fundamental question. So this is just an example that many people have been working along these lines, and this is just an example of a recent work from my group with Junji. As for realizations, what could be these hexagons, monomers? There are electronic degrees of freedom here, as well as, you can see in the sketch, a vibration or multiple vibrations. So in a coarse-grained picture, this could be, for example, base pair in a DNA molecule. So this is, again, just an example for my group, a project with Roman on charge transport through DNA. So moving on from conductance or current voltage characteristics, we have been interested in noise. And this is an example of a project with the experimental group. What they measured was short noise, electronic noise, but electronic noise that is activated due to temperature difference. So here is a setup of their experiment. I'm not going to describe it in detail in my talk, so this is really just a brief description. Again, 2 gold electrodes, and in between them a small molecule, and they apply temperature difference, as you can see from the color scheme, and measure the resulting electronic noise. And we assisted in the theoretical description. And finally, the last sort of aspect of charge transport are, of course, in the context of quantum thermodynamics, one central device or engine that you can realize is a thermoelectric engine. And where is it? Okay, here it is. I just wanted, of course, there are many aspects to this problem. I wanted to mention this inequality developed in relation to the thermodynamic uncertainty relation by Pietzonka and Seifert about 2 years ago. And again, we looked at this relationship with Junji, thinking about what it means in the quantum regime. So with this introduction, I guess I'm ready to give you the outline of my talk. So there are 3 parts. First, I'm going to focus on this paper, which was published, 2 years ago, but still I think there are several fundamental and important elements there that I would like to highlight. And furthermore, as we continue to work along these lines, we really built on that fundamental understanding. So I would like to go over the main aspect, the main component of this work. So it's a project with BJ, and the title is something along on the validity, assessing the validity of the thermodynamic uncertainty relation in quantum systems. And as you can see, I'm trying to minimize the quantum aspect here because, in fact, the main argument, or the most important argument in that work, was not necessarily regarding quantum systems. It's more general. It actually corresponds to the exchange fluctuation relation, and that's what I want to highlight here. And here is the thermodynamic uncertainty relations that I'm going to focus at, not the generalized one that we have heard, for example, from Gabriel Andy, but this form, the specialized or the specific form. So I will spend quite some time on part 1, and then as time allows, I will talk about 2 extensions, one in the context of thermoelectric junctions, a project with Junji, and the other one in the context of heat transport. I will be very brief on part 2. And then finally, I will mention measurements. So this was done in the group of Oriental at the Weizmann Institute with Ophir, the graduate student who performed the measurements. And there are 2 studies here that I will describe. As you can see, the first one, that's a project with Anki. It's actually about the anomalous short noise. Indeed, in order to explain what we did regarding the tour in atomic scale conductors, I will have first to tell you about anomalous short noise, and then I will describe this project. And finally, at the bottom, I'm not going to talk about this project, but hopefully BJ could describe it. It's another measurement of the tour in a totally different setup, not this one, rather studying heat exchange, energy exchange between qubits in an NMR setting. So that's something else, and I will not talk about it. Hopefully he could contribute. So I'm going to focus on the standard tour. We've heard this beautiful talk by Gabriel, and there are other studies on the generalized bound, but I'm going to focus on this one. So that's a cost-precision trade-off relation, first derived by Barato and Seifert in this seminal now paper, and this derivation was based on Markovian dynamics. Yes, it's a classical argument based on a Markovian assumption. So what do we have here? We have the entropy production rate, Boltzmann's constant, and the relative fluctuation. So that's second cumulant and the average current square. Now this bound, as we know, is not universal. And there are, as we said, they are generalized bound. So of course, the first questions that I have to answer is, why bother with this one? Yeah, it's not universal. Who do we care still about this one? So in my talk, I will try to argue that this bound deserves our attention. It's quite interesting for several reasons. First, obviously, it's tighter than the generalized bounds, which means that indeed, in some cases, we can violate it. But some models do satisfy it beyond the Markov case, and that's intriguing, and we would like to understand the class of models that do satisfy it. What I will show you in the next few slides is that this left-hand side, which we refer to as the tour ratio, In fact, overall, the inequality, we can develop it perturbatively from equilibrium based on the exchange fluctuation relation. So we can understand more what the specific or standard tour means based on the fluctuation relation. Now, one aspect of this bound that I feel is quite important and why it's useful is that when we have a universal result, that's beautiful. Yeah, we all have universal results in physics. That really brings us joy. On the other hand, when we have results that are not universal, that we can violate, that's when things become more messy and more interesting, because then you can think about the different classes of dynamics and how they, whether or not they validate the bound, and what does it mean, if we violate them. So that's indeed one aspect in favor of looking again at this bound. Okay, so that's a paper I'm going to discuss in some details, assessing the validity of the thermodynamic uncertainty relation. And again, I cross the quantum systems because the main argument is not necessarily for quantum systems. So here's the thermodynamic uncertainty relation. There could be different currents, but here we are going to focus on this setup where we just have two terminals, two electrodes here, and a single affinity. We just apply a bias voltage V. And we focus on the steady state regime, and it's all about charge transport. So what you see here is whatever conductor, here it's okay, it's designed as quantum dots. And as for the electrodes, with the gray clouds, I tried to imitate the different chemical potentials. And the system is at finite temperature. Do not assume zero temperature, that's important. So this is a tool as written generally, but now in this system, the entropy production rate is given by the current times the affinity, just the joules heating, and once we substitute the entropy production rate here, this is the inequality that we gather. So we have beta as the inverse temperature, V as the applied voltage, and now just the ratio between the variance, the second cumulant, and the average current, and that's the inequality that we are going to focus on. Okay, so how do we think about it? So we have the current and we have its noise, and we would like to look at the ratio between them. And I'm going to assume that I can write this series expansion, assuming that the current and the noise, they don't show any divergency, nothing too critical. So here's a general series expansion where the current is given in terms of the linear conductance and then the quadratic coefficient and so on and so forth. Of course, some of them can be zero. For example, if your system cannot act as a diode given symmetries, G2 would be zero. So some of these coefficients are not necessarily non-zero. And a similar expansion for the variance. So S0 is equilibrium noise, and additional coefficients, S1 for the linear coefficient, and so on. Now, what do we know about these transport coefficients? We know that the equilibrium noise is related to the electrical conductance, to the linear response conductance. So that's a fluctuation dissipation relation, or what we also refer to as a Johnson-Nyquist noise. Similarly, we have relationships between higher order coefficients. For example, S1 is proportional to G2. And there are many such relationships. So where do they come from? Let me quickly tell you, if you are not familiar with this argument, these relationships come from they can be derived from the exchange fluctuation symmetry. So here is our setup, and based on the initial conditions and the dynamics, the reversibility of the Hamiltonian dynamics, we satisfy the exchange fluctuation symmetry. So what is written here, N, is a number of electrons that are exchanged within a certain time interval, T. So the probability to transfer N electrons against the bias voltage is exponentially suppressed. That's what this relationship tells us. And we know that we can write it, instead of with the probability distribution function, in terms of the cumulant generating function. So this fluctuation symmetry can be written for chi, the cumulant generating function. And alpha is a counting parameter or counting field. So I just need you to focus on the last relationship. This is chi, the cumulant generating function in terms of the counting parameter, and we can write it in this expansion with the different cumulants. So where are the relationships? This was done by Saito and Otsumi in this very nicely in this 2008 paper. So very quickly, how do we achieve them? So here is the expansion for the cumulant generating function, and here is the symmetry that it satisfies. And what I'm doing between first line and the second is just expanding the cumulants, again, as I showed you before, in orders of the applied voltage. So these are the coefficients where K identifies the cumulant and L is the order in voltage. And now as we use the symmetry, the fluctuation symmetry, I'm just shifting the alpha in this manner. And what we have to do, and I'm not going to show the details, we just have to equate from the left-hand side the coefficients with the same power in voltage. So we have to collect the different coefficients, and this is what you eventually get. And that's a very beautiful relationship between different transport coefficients. So what you find is that for the K cumulants, the L power coefficient is related, as you can see, to the different cumulants with different coefficients in voltage. So that's, as you can see, these relationships really come from the exchange fluctuation relation. So I'm back with these two. They are just the first two relationships. But as I've said, in fact, you can continue in this manner and derive many, many more relationships. For example, C1, which corresponds to skewness, is related to S2 and G3. And that's going to be important for our discussion. C0 is actually 0. So, okay, so back to the two. Now that we understand that there are, or we recall that there are all sorts of relationships between the transport coefficients, remember my specialized or 2, that's a ratio of the noise to the current that I was interested at. Here it is, that's the left-hand side. I want to emphasize that it's more general than the just Fano factor. The fact that you have here beta, the inverse temperature, and V, makes this expansion more tricky, or you just have to be more careful. So what we do, we just take the expansion for the fluctuation and the expansion for the current, we put them together and we collect terms order by order in voltage. So that's a zeroth order term. And using this relationship, you can show that it's just 2. And then if you look at the first order expansion based on the second relationship, you gather that it's actually just 0. So the first order expansion here disappears. And as for the V square, again, you can collect terms, you can organize them based on these relationships. And this is what you get overall. So it's 2, and then, as I've said, the linear term disappears, and the first non-trivial term is order V square. And what is hidden here, sorry, too much notation, but here it is. What is hidden here are just the S2, here it is, and the G3. And in fact, what is hidden here is precisely the skewness, the first term in the skewness. So that was, I would say, the main result. I'm just summarizing this result in this slide. That was the main result in this paper, which I think is quite powerful because it shows you how the, what you may call the standard tool or the specialized tool is actually, it's rooted in the fluctuation symmetry. So what did we see? Okay, again, the left-hand side is given by 2, V squared term with the skewness. And this argument, this derivation is valid for classical and quantum systems. Now, the main point is that this combination is not necessarily positive. So if we think about the inequality where we have had the left-hand side greater than 2, greater or equal to 2, now we realize that actually this term can be negative. It really depends on the underlying dynamics, on the probability distribution function for the process. And if the skewness is negative, you go below 2. And of course, there are other terms. So even if this is still positive, you could see violations coming from higher orders. But that's the main observation, that we can already understand violations of the standard tool based on the skewness. And as I've said, this argument is not limited to whether classical or quantum systems. We didn't make any, we didn't specify whether there are many body interactions in the system, asymmetry, system bath coupling, it can be strong, and all sorts of quantum effects are allowed. And similarly, the temperature, we didn't limit it to high or low temperature. So in a way, that's why that's the main result that we used in subsequent studies. The two the standard tour can be violated based on the sign of the skewness. You really have to understand what it means. Definitely what is missing here is a direct relationship to the notion of Markovianities that we know was a key to the original derivation. So what I'm going to do next is just exemplify this result in a very simple model, non-interacting quantum coherent charge transport. So what do we have here? That's the same pictures that I've had before, but now electrons are non-interacting, and I'm going to assume it's fully quantum coherent. So for this scenario, in fact, one can derive the cumulative generating function, and it was done years ago, maybe 30 years ago, by Levitov and Lesovic. So that's this formula for the full counting statistics, where alpha, again, is a counting parameter. There are two functions that play here here. So one of them is, of course, the Fermi function, characterizing the left and right metals with different chemical potentials and a non-zero finite temperature. The second function, which plays here a role, is a transmission function, this T of E. So that's a probability for an electron incoming with an energy E to cross a system. It depends on the structure or the electronic structure of your system. Yeah, if there are different electronic states, everything is embedded within this transmission function. Furthermore, it depends on the coupling strength between your system and your electrodes. And we will see some examples immediately. So based on this Levitov-Lesovic formula, we can derive all cumulants. And here is what we know as Landauer's formula for the current, and we also have an explicit expression for the variance. So what we are going to do, remember my expansion. So that was the ratio, that was essentially the left-hand side of the tour. And in our perturbative expansion in orders of voltage, we have had 2 plus v square and the skewness, and this is what you get for this particular model or a particular setting. I haven't yet specified what is a transmission function. Yeah, it really depends on the details of your structure. So in order to find out whether or not we satisfy this specialized relationship, whether or not we can go below 2, we need to understand the sign of this function here at the right-hand side. And essentially, it's what we have in the bracket, in the square bracket, which is going to determine the sign. So, as I've said, we have these two functions, the transmission coefficient, which can go between 0 and 1, but it doesn't have to reach 1. It can go well, yeah, it maybe whatever your system is, it can be actually quite small. And this derivative of the Fermi function, this is also, you can organize it as the same function. And here, and it's bounded by quarter, 1/4. And here is how it looks like. And the width is determined by the temperature. So just to illustrate, I plotted here the two functions in, as one example. So that's transmission probability. It can actually have a rich structure depending on your system, but here as an example, it's a Lorentzian shaped. Now the width of this function is dictated by the coupling strength of your system to the electrodes. So in this example, the temperature is high relative to this width parameter. But of course, you can be in the opposite scenario where the temperature is low and this function is broad. And that's actually what we have had when we looked at atomic scale junctions. Yeah, so these are the two functions, and we have to understand together, how they work together. So to understand the sign of this coefficient, which dictates, the validity of the two. So there are, just to mention, before we get to examples, there are several limits that are interesting. And actually, we can address them analytically and try to understand what they mean for the two. Low transmission. So if the transmission coefficient is very small, meaning that in terms of electrons, probability to cross a system, it's small, well below 1, then we can actually neglect altogether this contribution. Because note that we already have transmission probability here, so transmission square is going to be small. We can ignore the second part. So that's one limit which you can try to connect to Poissonian dynamics. Second limit, constant transmission. If the transmission probability is about constant, so this function is very flat relative to the other one, again, we can solve the problem analytically. And the other limit, which is actually depicted here, is a resonance tunneling condition. If this function is very narrow, we only have to evaluate this Fermi function, derivative of the Fermi function, at the resonance energy. Yeah, that's the main contribution to the integral. So indeed, we can, just to show you some results, we can evaluate the Tour, this inequality, this second term that dictates the sign of, or the validity of the Tour in different limits. The low transmission, as I've said, we just ignore this part, and we find a positive contribution. So the Tour as a whole is valid. Yeah, the inequality is satisfied. If you look at the left-hand side, it's greater than 2. If the transmission is constant, we get something which again is all positive. So we have a suppression which is quantum suppression, but overall the Tour is valid. And the last case here is what I mentioned, the resonance tunneling condition, when the transmission probability is very sharp. And here's where I want to highlight what's going on, because it's quite interesting. You can simplify what's going on here, and you find that the condition for violation, or the condition for the second term to become negative, is when T2 is greater than 2/3 of T1. T2 is a transmission squared integrated, and T1 is just a transmission itself integrated. So what is the meaning of this condition? I cannot really explain the 2/3, but what is the intuition behind? So we are going to violate the Tour. We know from the derivation of Barato and Seifert that it's related to Markovianity. So what is T2? T2, you can think about it as co-tunneling process. Yeah, it's transmission squared, coordinated motion of 2 electrons in your system. So if T2 is too large, yeah, if it's greater than 2/3 of T1, the contribution of these processes is too significant, then you are going to violate the Tour. So you see, you don't have to be strictly Poissonian, if I may think about that. You can go beyond that, but not too much. Yeah, not too much of the T2 contributions. So that's, I guess, an interesting outcome of this derivation. Very quickly, I will talk about, let me mention realizations. So if you think, and that indeed helped us to think about experiments, experimental advances in quantum dots, there are of course many nice experiments. So the question is whether they could realize this, or they could assess the validity of the Tour. So here are some examples: single quantum dot, serial double quantum dot, or side coupled. I will not go over all the details, but just as an example how the transmission probability look like as a function of energy. So for the single dot, it's just a boring Lorentzian. While for the double dot, for example, you get this double peak. But if the gamma, which is a coupling strength to the metals, is large, as you can see, this peak is suppressed. So the transmission actually is way below 1. So that's the limit of small transmission probability. And you can think about it as an interference process, destructive interference. So a quick example, and what is the message that I'm trying to say, not just showing you some data. So we show that, yeah, you can violate the standard Tour, which is, well, not too surprising, but it's still interesting to understand when it happens. But the second question is, well, you violate it, but is it really dramatic? Yeah, to what extent you violate it? And what we found, which is quite interesting, I think, is that there are violations, but they are not very dramatic. They are still quite minimal. In fact, when we first started to perform simulations, we thought that we were just not doing great numerics. That it was just a numerical issue with the violations that we observed. So they can be quite small, which again I find is something that we should understand. What is the actual bound to these violations? So here's a case of a single quantum dot, and if it's negative, it means that there are Tour violations. The standard Tour, I'm talking, of course, as a function of gamma. You can see, well, when gamma is small, everything is positive, so the standard Tour is satisfied. But it's violated here at large gamma. And again, I want you to look at the values. It's small. Yeah, so these violations are not dramatic. To a great extent, you are almost satisfying the Tour. And similarly for the serial double quantum dot, here I want to emphasize the regime of when do we violate it, which is quite interesting. So what are the parameters? We have the gamma L and gamma R, which dictates the coupling strength to the left and right electrodes. We also have the energy levels, which we are going to assume are degenerate and actually set at exactly the Fermi energy. And omega, which is a tunneling, hopping energy constant here. So again, the sign here dictates this violation of the standard Tour. And as you can see, when it's negative, we do observe violations. Now, omega here, I should have mentioned, is about the same order. It's about 0.05 here. So you see that when the internal tunneling and the hybridization constant are about the same, that's when we observe these violations. So it's a tricky regime. Actually, I don't have a good intuition of what does it mean in terms of dynamics. Why is it Tour satisfied at stronger hybridization or weaker? But there is this interesting intermediate regime where we violate it. We can justify it or at least rationalize it based on the behavior of based on co-tunneling processes. So remember my point about T2 greater than 2/3 of T1. T2 measures the extent of co-tunneling processes, and indeed, this is precisely the region where T2 is too large. So so that's for this paper. And again, it's all about this, what I refer to as a standard tool. They are not the generalized one. And the main points that I'm trying to convey is that understanding its violations is actually very interesting because it allows you to more deeply understand the dynamics of your system. What are the different regimes for your dynamics? How much time do I have? Okay, I guess I'm still okay. So let me just mention 2 extensions. One of them was for thermoelectric junctions, and it was done by Junji. Very briefly, I will just mention one nice aspect of this work. So probably you are familiar with this extension of the tool by Pietsonka and Seifert from 2 years ago. Yeah. So here is again this sort of the standard tool, this thermodynamic uncertainty relation, and one can actually translate it into this inequality for the power fluctuations. Yeah, alpha should be for the power output. So we have this interesting inequality. J alpha should be negative when the system performs as an engine. So that would explain you the sign here. So what it tells us is that when you approach the Carnot efficiency, the fluctuations diverge, and it's directly derived from this inequality. How can you see it? Well, in this system, there are 2 affinities: the temperature difference, that's the color scheme, and also the chemical potential difference. And the entropy production is given by the sum of the current and the affinity multiplied by their affinities. And you define 2 currents for the charge current and the energy current. And from there you define particle current, the power output and the heat current. You can define the efficiency. And with all these definitions, you can actually transform this inequality to this one. So what Junji showed, which was quite interesting, was that first you can see here, here's a regime of violations of this standard tool. It's actually happening in a regime which is not interesting because the system acts as an engine here. Yeah, so when the system acts as an engine, broadly, the tool is satisfied. So that's one interesting observation. There is a tiny region, I don't know if you can see it here, of violation in the regime of when the system does act as an engine, and you can see it here. As I've said, when there are violations, generally we observed small violations. But what was still interesting is that as we approach the Carnot, again, the tool was satisfied. So there could be violations of the tool, but everything is satisfied as we approach the Carnot limit. So this is satisfied throughout in our system as we approach the Carnot limit. Okay, so the next extension, which I'm just going to talk about a tiny element of this nice paper, is about heat transport. And we analyzed 3 examples. Would like to mention something about the tool in harmonic systems. So what we showed here was that, in fact, the tool, which is written here for the system for heat transport, vibrational heat transport, is exactly satisfied. The specialized tool is exactly satisfied for harmonic systems, whether they are classical or quantum. You don't need to make any assumptions. If the model is all degrees of freedom are harmonic, the tool is satisfied. So that brings me back to my main argument about this specialized tool. It's true. It can be violated in certain regimes, but still there are several classes of models that satisfy it. And it's interesting to understand what that means. So you can see we don't need to make any assumption about the coupling strength, about the internal dynamics. The specialized tool is satisfied here. Okay, so with that, I'm going to move on and talk about measurements. measurements of shot noise, and this brings us also to measurements related to the thermodynamic uncertainty relation. This paper is almost published. This is the archive version. It should be published soon in PhysRevB. So the experiment was performed by the group of Oriental at the Weizmann Institute with his graduate student, and the data was analyzed by my graduate student, Chava. Now, here's again the tool that we are going to consider. I'm focusing on the same setup that I mentioned originally in the paper with the 2018 paper with BJ. So it's a single affinity two-terminal problem. We just apply voltage bias, finite temperature, and this is inequalities that we would like to test. So obviously, if we want to look at experimental data, we need both the average current and the noise. So this brings me first to think about the noise. And let me describe what the experimentalists have been doing. I encourage you to check the webpage of Oren. They have been doing very beautiful experiments. I will just mention this one. So they have been playing with a technique called the mechanically controllable break junction technique. And specific to our experiment, this is what they have. I will try to describe it to the best of my knowledge. These two pieces are just gold. And as you can see, there is a constriction in between. And what they do in a very controlled manner, they can break this junction by bending it, as you can see. And in the ultimate limit, they can reach in a controlled manner the limit of a single gold atom connecting the two electrodes. And of course, they can continue to bend and break it eventually. So that's what they have been doing in order to form these atomic scale junctions. And in fact, they repeat the experiment many times. They form such an atomic junction, they measure it, and then they break it and reform a new junction to perform the experiment on it. So eventually they have an ensemble of such junctions with their measurements. So what do they measure? They measure the linear conductance, and this is what you can see here below. Just focus on the gold histogram. So that's a histogram of the conductance. And as you can see, there is one peak centered around 1 unit in G naught, and this indeed corresponds, based on many other studies, we have the confidence that these junctions correspond to this atomic picture, with a single gold atom between the electrodes. So they can measure the linear conductance, the IV characteristics, as they push the voltage up to, I guess mostly in our study, it's up to 0.5 volt, and they also measure the electronic noise as a function of voltage. So this is what you can see here, the power spectra, the noise as a function of frequency. They have the low frequency component, which is interesting by itself, and furthermore, the white noise component. So, as I've said, in order to in order to test the tool in this setup, first we have to understand the shot noise in the system. So this project was done with Anki, a former undergraduate student in my group. And let me tell you, I have to explain to you what we found over there in order to explain the measurements of the tool. So here are, in these 3 panels, you see 3 different experiments, 3 different measurements forming such atomic scale junctions and performing noise measurements. So that's a shot noise as a function of bias voltage in 3 different examples, 3 different atomic scale junctions. Experiment in these blue circles, and the dashed line is just to guide your eye. So what do you observe here? First, even when the bias voltage is 0, as you can see, we do have noise. So that's equilibrium noise, the Johnson-Nyquist contribution. The temperature was about 10 degrees Kelvin. So that's the start. That's the first point here. And in the other example, it's the same. You can see the equilibrium noise. The next part of the spectrum of the noise is the normal shot, what we refer to as a normal shot noise. So it's linear in the current, in fact. These are ohmic conductors, and it's linear in the voltage. So roughly, I tried to circle it. This is what we observe here, and that's the well-known shot noise. However, as we continue to increase the voltage, we get to this green region, which is a little bit confusing. So sometimes the shot noise, as you can see, goes down below the linear trend. Sometimes it goes up, and so on. So in fact, every junction, we will see a little bit of a different behavior. And that's, we would like to understand it. We know so much about atomic scale junctions. We have the confidence that we understand what's going on in this region. And the question is, what's wrong? Yeah, what happens here? It doesn't seem to be universal. Different junctions show different behavior. Is there still a unifying explanation to these trends? We would hope to capture this variety of observations within a simple single explanation. And also, one important question is whether the coherent transport picture is still valid here. We know that we can use it to explain what's going on here. So the question is whether this variation corresponds to maybe the activation of vibrations in the system, heating effects, and so on. So that's what we set to do here. Can we still explain these observations with a unifying explanation that hopefully or that actually still builds on the quantum coherent picture? So I should say that these observations of what we refer to as anomalous short noise, it's not because the lab of Oren is not good, it's not because they are not great experimentalists. Other experimental groups had observed similar trends in similar systems and they published it, so there are a couple of papers from the last few years analyzing this anomalous short noise. But there was no agreement what's the source of this behavior. So as I've said, what we set to do was to still try to suggest a quantum coherent transport model that could explain this variety of observations. So our model still assumes that we can use this picture of non-interacting coherent electrons. So here's the current and Dvira's formula and the noise, and I just want to apologize, I switched notation for the transmission probability from the big T to the small, from the big tau to the small one. And now there are two building blocks in our models. I will be very quick here. One is that the transmission coefficient, this function, actually depends on energy. Of course, in the full expression it does, but when people explain the normal short noise, this linear trend, they just assume the transmission coefficient to be constant. That's particularly true for gold. But here, one component that we put into our modeling is that you do have to include this variation with energy because you are considering high voltage behavior. So if this is, say, the transmission probability, if the voltage is high, now the bias window is large, you have to take into account the functional behavior of the transmission function. And the second building block, which is directly related to the first one, is that the voltage may drop asymmetrically in your system. So, and this is captured, unfortunately, by the parameter alpha here. So it's not the counting parameter, it's just it's now newly defined. And when it's half, it means that the chemical potential drops symmetrically on the two electrodes, half here and half there. But as you can see, it can go between 0 and 1. If it's 1, it means that the voltage drops entirely on the left side. So usually when we theoreticians do calculations, we just assume, mu L is half, it shifts by half of the applied voltage, and mu R similarly by half, and that's it. But in fact, it really depends on the structure, and that's the building block that we put in our modeling. And it's a mean-field way to encapsulate a many-body effect. So your system, the electrons in the system respond to the applied voltage, and that's essentially what this alpha parameter captures. The fact that since the structure itself is not entirely symmetric, the electronic structure is going to respond in different ways to the applied voltage. So with these two components, again, I'm not going to dwell on the derivations, but we were able to derive expressions for the differential conductance and the short noise, and we have had new contribution coming because of this energy-dependent transmission function and the fact that the voltage may drop asymmetrically on the two electrodes, and we have these two contributions. And what we showed, again, without details, is that we can now explain experimental observations. So the experiment is the blue circles, and our theory was a dashed line for the differential conductance, and similarly for the short noise. So why do I tell you this story? Why do we care? It's because we need, if we want to understand the two now in these systems, we need to understand the behavior of the noise. We need at least to have a picture of what's going on, whether there is a reasonable model that we believe can explain these observations. So this indeed brings me to the final part of my talk in the last very few minutes, these measurements of or testing the uncertainty relation. So essentially we have the current, we have the noise, now we can put them together and just build this left-hand side. We refer to it as the Tour ratio, and we can test whether we satisfy this inequality. So this is a short, simple paper, simple manuscript, a little bit of a theory to show that based on the experimental parameters or the temperature, the applied voltage, we do expect this inequality to be satisfied in this system, and then some measurements showing indeed what they get. So what do they measure? Just many data points, but just to quickly show what is the data that we get from the experimentalist. So these 10 panels are 10 different junctions that they form and perform measurements. And they ignore the color scheme. This the pink or blue, just different experiments of the measurements of differential conductance. And for each junction, they furthermore measure the IV characteristic and the corresponding noise, short noise. So that's the data, the bulk of the data that Chava took and analyzed, and she put it together to analyze the tour. So I think I will skip this slide and I will go immediately to the last one. So this is a tour ratio. And analytically, we argued that in our system, this is how it should look like. So it begins by 2, which is the equilibrium value. And then we have a linear term in voltage with the inverse temperature and the equilibrium Fano factor. So this is sort of universal, may I say. But then there is a next term, which is really, it comes from this anomalous short noise contribution. So it encapsulates, again, the structure of the system. And as you can see, the sign, gamma, actually can be either positive or negative. It depends on your junction. So the sign here can be positive or negative, which potentially can lead to deviations from the standard tool. So very quickly, so that's indeed the data. The data is a diagonal, and the 2 lines are equation 10, where the dashed line is when we include this contribution, and the full line is when we ignore it. And you can see the data sort of interpolates between these 2 limits. And so what's the message? The message is, first, we satisfy the 2. I don't know if it's bringing you great joy, but the system, as we expected, also theoretically, it does satisfy it. More fundamentally, we believe we can understand the different transport regions here, the linear short noise, the nonlinear behavior. And this is really a proposal for people to continue and look at this type of experimental setups and continue with the studies of whether inequalities or basic relationships coming from stochastic thermodynamics. So we believe that these structures and atomic scale junctions are maybe a little bit boring because the transmission coefficient is quite flat, but moving on and doing related experiments with molecules where transmission coefficient is very rich and interesting, one could see maybe more interesting behavior for these relationships. So with that, I would like to conclude first the measurements. The tour is satisfied. We did include many body effects in this mean field treatment. The tour ratio, as we refer to the left-hand side, it may assist in identifying transport mechanisms. It develops from 2. Then we have the normal short noise region and the anomalous short noise region, here and there. So that's also a nice way to organize your measurements, short noise measurement, on this universal type curve. And then more generally, just concluding my talk, I guess I'm just on time. So I try to convince you that this standard, as I refer to it, the standard tool, actually we can understand its origin based on the exchange fluctuation relation, and violating it is also quite interesting because you can try to get into the dynamics and understand the probability distribution function. We don't really understand the connection between Markovianity, or whether it's even quantum Markovianity, and this tool. Of course, implications for performance. Many body effects here, we took them only in a mean field manner. And finally, this brings us back to an effort in my group to develop methods, rigorous methods, to calculate current, noise, heat exchange, and other questions in quantum thermodynamics. So with that, I would like, again, to thank you for the invitation to present my work, and to thank the collaborators and the students, and I would be happy to answer questions. Thank you.
Thank you very much, Dvira. That was really good. Thanks for such a clear talk. Now we have plenty of time for questions, guys, so please feel free to ask. We already have a question from Mauro Patanostro. He asks, could the anomalous behavior be linked to changes in the conformation of the specific junction being used? Apologies, this is likely an incredibly stupid question, he adds parenthetically.
No, so that's that's actually a good question. It's not silly. Let's take a picture. Maybe here, maybe just this diagram. So we think between experiments, that the conformations are different. That's precisely what could happen. So they form a new junction. While they do, based on the measurements of conductance, they believe there is one atom. It still can be, the junction region can be slightly different. Actually, what we are still missing is indeed a connection between the atomic picture and the differential conductance and the noise. Some people have performed simulations, but I feel it's still a missing link. Now, within the measurements, we don't think there is an actual change in the structure because they repeat the measurement of the conductance after the noise measurement to ensure that there was no structural change during the measurement, if that was a question. But example to example, these are slightly different atomic structures. Exactly.
Thank you. Okay, so we have a question from Gabriel Langi. He says, "Hi Dvira, thank you for the fantastic talk. Could you please comment more on the relation between non-Markovianity and the ratio T2 over T1? Somehow that feels strange."
Oh, I don't have a good answer to that. So that's this is this part. So first, just to repeat where this came from. So we have had this perturbative expansion for this ratio. There are more terms here, so we should put additional comment for additional terms. So that's a v squared term. And here we just analyzed when can this become negative. And in the resonant tunneling condition, so it's not it's still limited to when the transmission is quite narrow relative to the temperature, then we can identify mathematically this relationship. And now it's indeed an interpretation. So we found that this is going to be negative if T2 is greater than 2/3 T1. And now comes my interpretation that T2 indeed corresponds to co-tunneling processes. So it cannot be too large. So Markovianity, I would say, is related to Poissonian dynamics, where I have independent processes, while T2 corresponds to a coordinate process of two electrons, coming together. But that's precisely where we also have a missing understanding of the relationship between these two notions. The Markovianity coming from the classical study of the paper of Barato and Seifert, and what we see here in this expansion, which we don't need to think on Markovianity.
Thanks a lot. Maybe I can ask a follow-up question because I was also interested in this. I mean, because these are non-interacting particles, right? So usually you think about them as not having any correlations between them. So, I mean, are the correlations between tunneling events here related purely to Pauli exclusion? Because, I mean, would that explain also why you don't see violations of TOR in bosonic case? Or is that completely off?
I guess it's true, because the second term, as you can see, you have the F1 minus F. So, these are non-interacting electrons. But as you say, the Pauli exclusion, you can see it here with the F1 minus F factor. And we don't see it indeed for bosonic systems. So you are right in this interpretation.
I mean, it would also explain why you need a kind of tight transmission function, because otherwise there'd be very little probability of two electrons with the same energy trying across at the same time, I guess, right?
So, when the transmission is very small, the probability to transport is very small, the tour is valid throughout. I have to think about the constant transmission limit.
But I guess it's like it's very unlikely for two electrons with the same. I mean, basically the majority of the current comes from electrons with two different energies, right? I mean, if they can go across at all different energies, they wouldn't really overlap. This is a bit heuristic, but
So, but just wanted to make also the point that the low transmission limit, when just the probability to transport is very small, that's when we see it fully satisfied.
I see. Thanks very much. So sorry for interjecting there with just my question. So we have more questions from the audience. So John says, thanks for the great talk. He says, naively bringing intuition from the nice expressions from expansions for so he's just saying he's naively bringing intuition from the nice expressions for expansions from quadratic systems. you could either look for violations of standard TUR by adding non-quadratic interactions in the working medium, but also looking beyond non-interacting fermions in the leads, i.e. by exotic distributions of electrons. Do you have any intuition for this?
Okay, so I would like first to just highlight that, okay, the equation is not written really nice. The transport coefficients, S2, which was coming from the noise expansion, and G3.
Sorry, Dvira. I just noticed that we suddenly got disconnected there for a few seconds, so it might have cut off your answer. Would you mind? I'm really sorry. Would you mind just going back to the beginning of the answer to John's question, just because I think it would have got cut off?
Yeah, I wanted first to highlight that this inequality, okay, it's not written here, it's written as an equality, not great, but the left-hand side is equal to 2 plus v squared, and then the skewness. First, what is inside here, I haven't specified in the general derivation. So S2 is just the coefficient for the v squared in the noise, and G3 the coefficient in the conductance. So yeah, this is general. So this could be negative if the skewness is negative. This is negative. So many systems could show that. And of course, the question is, I guess that's what John is asking, whether we have we can suggest models that indeed would show violations related to many body effects. So yeah, that's where we are missing. So what we would need to do is full counting statistics for many body systems, yeah, to be able to get such an expansion for the different cumulants, and then find out whether this is negative. But of course, the question is, physically, we understand the relationship between the underlying dynamics and the structure of the probability distribution function. So that's actually what the standard tool tells us, that the skewness, if it's negative, you violate it, at least to that order in v squared. Yeah, but designing many body models that could show negative skewness and understanding why, yeah, that's indeed something that we would like to do.
Okay, thanks very much. Okay, so we have another question from Andrea Timpanaro. Also building on Gabrielle's question, would T of epsilon similar to 1 mean that the electrons are highly... Sorry, I think he means the transmission function. So would transmission function similar to 1 mean that the electrons are highly correlated?
No, so transmission close to 1, actually this is what we observe for these gold junctions. If the energy dependent is very weak, you can rationalize it as a very strong link between your conductor. If you think about quantum dots, it's tightly connected to the electrodes. So actually what happens here, the large transmissions that we see in the atomic scale junctions let me show, sorry. Yeah, here for example, so transmission is almost 1 here, and it's actually quite flat in many cases. Still, you would say these are single electrons. It's more because of the structure, the strong connection between the atom at the center and the electrodes.
Okay, thanks. Yeah, I mean, another way I guess you could think about it is, I mean, transmission function being flat means probably the lifetime of electronic states is really, really short. Wouldn't that be kind of correct? So they have very little chance to actually get correlated with one another going through the junction.
Yeah, so it's a very large gamma, you would say, which is small lifetime. Yeah.
Yeah. Okay. There. Thanks a lot. That's actually really helpful and for me to understand this now. Thanks a lot. Okay. So now we also have a question from Paul Eastham. Hi, Paul. He asks, so hi, Dvira. Thanks for the great talk. A similar question to John's, perhaps, but I wonder if the connection to Markovianity might arise if it were true that Markovian dynamics implies a Gaussian P of n, so probability distribution.
Oh, yeah. So if we have a symmetric distribution with no skewness, then we are good. It's satisfied. I guess that's his question. So the term that potentially shows violation is related to the skewness, which is an asymmetry of the probability distribution function. And if this probability is fully symmetric, then, I mean, if it's a Gaussian and we don't have the skewness, then, where is it? Sorry, I'm going back. Then it's satisfied. Does it answer his question? Yeah.
I guess he was also asking about the connection to Markovianity, right? So is a symmetric P of n related to Markovianity at all, or doesn't seem necessarily so?
Gaussian, yeah, if it's Gaussian, then we are good. But generally, no, I wouldn't say so. I mean, it could be a symmetric distribution, but with higher order moments that could contribute higher and higher terms and potentially still show violations if they are negative. Yeah, I don't know. So yeah, we are missing generally this link between the dynamics, the probability distribution function, and the notion of Markovianity.
Okay, thanks very much. Okay, so if we have any more questions, maybe just while we wait for maybe another question, I can just ask. I mean, do you? Sorry if you kind of already mentioned this, but it's not so yet sort of clear to me. I mean, do you think from even just sticking with the case of non-interacting kind of electron transport, I mean, is it sort of clear what the design principles would be to kind of minimize fluctuations in general, or is it a little bit? It's a bit hard to give a concise answer to that question. Maybe I don't know.
So at least the intuitions that we got from the atomic scale junctions, yeah, in some cases, the anomalous short noise shows suppression from the normal noise. Yeah, so that's a suppression of fluctuations at high voltage. But yeah, we don't have the atomic picture to that. So I'm not sure what it means in terms of structure. Why do we have? It's actually something that we would like to do, to take atomic pictures. I mean, in terms of simulations, and try to understand the suppression of the noise at high bias. What does it mean in terms of structure? Now, I'm trying to recall, there were also studies of noise, of course, with molecules, and they have a very rich transmission structure, but I don't remember what did they see for the short noise in terms of suppression or enhancement. And of course, once you couple to vibrations, there is also a nice literature about what the role of vibration could be. When it can activate, it can add to the noise, but there are also steps of where it reduces it. It really depends where you are at the conductance. There is no, I would say, clear, definite answer to that. Maybe yet. Yeah.
Okay, thanks. I suspected as much, but yeah, thanks for the answer. Okay, so it looks like we don't have any more questions. We have of course lots of virtual clapping from the audience and lots of thank yous from everyone. So I have to relay that over to you. But I think maybe it's a good moment to conclude. So thanks everyone for joining us once again, and especially thanks so much Dvira for giving us such a nice talk.
Thank you again, the organizers, for this really nice seminar series, and I keep watching it. And thanks everyone who participated.
Great, thanks.
Okay.